Hello, my name is Norman Brees, and I am going to be going over some information about what I do. So, to give you a low intro as to what my education is and what I'm going to be talking about is question is, have you seen the movie Ant-Man? Well, let's say that you're Ant-Man and you're going into the machine and it shrinks you down and it keeps on shrinking you and shrinking you and shrinking you and shrinking you past all the little stuff, and it ends up putting your feet on the nucleus of the atom. Okay, you're now standing on an atom and you're looking out at the electrons that are rotating or circulating around the nucleus. And you are observing their distance, you're observing their strength, you're observing their pull on the nucleus, and then you notice the atom that is across from you, and you notice the electrons on the outside of the atom that you're standing on, and the interreactions of the electrons of those electrons with the electrons of the adjacent atom. That's where my specialty is. My specialty is it's called either quantum physics or nuclear physics. So anyway, we're going to be going over some information from video by Neil deGrasse Tyson. I really like the way that he puts information across, and I'll be giving a little bit of feedback on what he talks about. So I'm going to go ahead and start playing this now, and then we will stop it when it's time for me to respond to it. Okay, here we go.
This is
So far, so good.
It's going good. All right, so I want to talk about Earth's magnetic field,
All right, already you got me.
if I may.
Yeah, this is good stuff already.
Okay, so we all know it has a magnetic field, and you learn that as a child when you have a compass, right? Particularly if you were in one of the Scouts programs, you have a compass, and the needle points north, and so that's north. Okay, so the north side of the needle points north, and that's how you know it's north. So let me start out by saying we all know that in magnetic fields, opposites attract, right? You knew this.
Yes, well, you take the north and the north, you put them together, and it's very cool because
They repel.
yeah, and then you have magnet races. This is how you have magnet races.
Push them
across the table. Yes.
I love the way they play off of each
That's how you
other.
have a magnet. Okay, so if you
around, then the north sticks to the
And
south. Okay.
right.
So what that means is, if the needle on your compass is magnetized north, then it's actually pointing to the Earth's south magnetic pole.
Right, that makes sense because
It
that would be
means
the opposite.
what you calling the
of
North Pole is
Is
actually
not.
the South Pole.
Right.
I just want to start there.
Wow.
Okay.
See, I'm just going to stop it there. Later on, when I get into talking about the quantum mechanics of the magnetic field, as I will be presenting them, and we'll be discussing the charged particles, to remember at that point that the charged particles are polarized, or that they're they're either going to be attracted to other particles or they're going to repel them. And here he's talking about that, about the magnetic field and the magnetic fields, as we make them dynamic, they'll be moving, they'll be rotating, and the particles. And later on, I'm going to show how the particles move about the magnet, that they have a specific rotation, they have a specific direction that they go. With the Earth, I like to refer to the Earth as a diamagnetic, diamagnetic sphere, where, as he's talking about, that the Earth rotates around the sun, and that he's going to get into. I'll tell you what, I'm going to place a little bit more, and he'll explain this, and then I will make more comment on it.
Okay. Thanks for ruining everything. And now I don't know what to believe
Okay.
Period.
Right. Earth's south magnetic pole is in the north because all north magnetic poles point to it.
Right.
Okay.
Interesting.
So I just didn't know if you knew that.
You know what?
And
I
don't
know
shoot
it-
the messenger.
I
Ain't
know
my
it
fault.
now, and I got to tell you, I wish I didn't.
He's a teacher with a lot of humor there.
So
No, that's actually very cool.
But wait, there's more.
Uh-oh.
Okay, so Earth's magnetic
Can we get
field
into it?
is not aligned with Earth's rotation axis. Okay, so Santa Claus is up there on the North Pole, all right? And your compass doesn't actually point to him. Okay? Well, it does point to him if you're exactly on the longitude where the North Magnetic Pole is found. If you are anywhere else, you are not pointing to the top of Earth's rotation axis. You are pointing to someplace in northwest Canada.
It's approximately 17
because
degrees
our
off.
magnetic pole
It is tipped relative to our...
And I'm going to get into that later on, so pay
So
attention.
the Earth sits, if you ran the pole, an actual pole through it,
If you did
sits
that.
on this tilted axis.
It's tilted. That's
So here's the sun, here's the earth like this. The earth is going around the sun at an angle.
And by the way, I in the scout manuals, when they
And
talk
this
about
is
the
the
use of-
device we use to find our way when we're lost.
He's talking about the compass, and so your magnetic compass is actually the south needle on the compass is actually pointing north because the opposite charges are attracting. Kind of funny.
Right.
Louis' house, you know.
Right. Now that's my cousin. That's my cousin Boo.
right when you get to cousin Boo's house, we'll make
I'd fast forward this, but I lose it, and they're fun to watch.
Right.
So
So anyway,
what the manuals for using a compass know about this, and it's called an offset. So depending on where you are on Earth's surface, when you whip out the compass, you would put an angle offset to find out what true north is.
yeah.
But that changes depending on where you are.
12 to 17 degrees off of north.
If you knew where you are on Earth,
You wouldn't need the
The
compass.
compass in the first place.
In the
Absolutely.
first place.
That's like people say, "I lost my keys." Well, where'd you leave them last? What? What?
Okay, so I'm going to fast forward this just a little bit. They talk about some fun stuff here. See if we got this
where
here.
the poles are and what the grid system is like. Compasses are basically completely obsolete. Plus,
Okay,
if you know
good.
any astronomy, you'll know which way north is and which way the sun
Yeah,
is.
the
pointing,
Big
right?
Dipper. We know how to look
the
at the Big
compass, I think,
Dipper
is
and find
overrated
north.
in this regard. Compared
So
with
I'm
other
going
ways you can-
I'm going to fast forward this a little bit more.
Here,
Here, the world is going to end and Earth's axis is going to
Okay.
flip. 'Cause they
Okay,
heard
so they're talking about here about the magnetic field of the Earth flipping. People think, oh, they're talking about, oh, well, the Earth is going to flip upside down. No, the Earth doesn't flip upside down. That the Earth remains the same. And they're talking about the charged particles coming off the sun, the solar winds, the explosions off the solar winds. Tyson here talks about the idea that these winds that come off of it, that sometimes are positive and sometimes are negative. And depending on which one, and they hit the Earth, and it's going to give this particular charge going to the Earth. And by the way, the Earth, the Earth, North Pole, South Pole, okay, guess what? Well, the charged particles don't go into the north first, they go into the south first. And they go through, and we're supposed to have an iron core, and it's supposed to come out the north, but the sun coming off with the solar winds is going to hit both at the same time, but it doesn't hit it north like that. Santa Claus doesn't get it first. It comes and it goes around like this, both at the same time. Aurora Borealis, and then the Aurora. I'm sorry, I forget what it's called for the southern end, and it goes through. It is the Earth is just a big magnet. It's a dipole magnet. That's what we're talking about. So we see the Aurora Borealis, we see the southern hemisphere aurora, and they help us to understand that we just live in this huge magnetic field. wonderful thing to understand. And so, so as he's talking about this, that we need to understand that everything about us is this magnetic field, and the magnetic field, and we can go into this later on. The magnetic field, it has the electrical part, and it has a magnetic field, and electricians know when they put their little device around a wire that they're measuring the ohms or the resistance, the workload of the wire. Well, guess what they're measuring? They're measuring the magnetic field around the electrical wire. And guess what? Our heart also has the electromagnetic field in our circulatory system and our lungs and everything. It all has the same thing. It's the electromagnetic field. You eat potassium and salt, you eat bananas and salt, and you charge your heart. You're charging your magnetic field. Yes. And so the EMF that everybody's also all concerned about, it's going to shut everything down. No, it's the way we live. We live this way. The magnetic field energizes us. It energizes the earth. It energizes all creatures around, and they get in and they're talking about this. And so, to the whole concept of the charged particles that he gets into later on is, if you have the particles that we all have, the atoms around us, and you put an electrical charge into those particles, you charge them, and now they are charged particles. Okay, now they are charged particles. And the charged particles, they get polarized and they line up. Before they're going, and now they go, and they line up because they're polarized. And now you have charged particles. Quantum physics. Yes, okay. So quantum physics means that all those particles, all those electrons, they know their position because the electric has come through and polarized them, and they have their job. Okay, and the job that they have, we're going to discuss later on, that the magnetic field, as it goes electrical, magnetic, and so on, that they operate in a wave at the speed of light. In science, it's called photonic energy. It's a byproduct. You put gas into your car, and the byproduct is exhaust. With this, you get the electric and the magnetic field, and they're going along like this, and their byproduct is light, photonic energy. And so later on, when you're driving your car or flying your car and it is being propelled by this, guess what your exhaust is going to be? It's going to be light. Yes, you'll produce light. They'll know that you're going along because you'll have a stream of light, and it won't be exhaust. It'll just be a stream of a beam of light. Star Trek, have a beam of light. And so as we're going along to this, it's important to understand that the charged particles, really, really, really simple. They zap them with electricity. And they go, and then all of a sudden they're polarized, and you get another one and go, and then they have the same pole, then they go, and the metal can't touch each other because the charged particles are going boom, just like your magnets do. You try to push them together, if they're the same pole and they don't touch, no collisions in the future because the charged particles are going to keep the vehicles apart. Sorry for all the auto body shops there, but you'll have another job. Okay, so I think that this is a really good introduction as far as charged particles. Quantum physics, it just means that it's really tiny at the atomic level. And charged particles, it's really quantum mania, and it's out there. It's simple. It's just something that they don't teach. They don't teach it in college because electromagnetic field is something that you can't see with your eyes. You can't hold it with your hands. You cannot put a machine on it to test it. And up until the last, Nikola Tesla did a lot of study on it, and Albert Einstein did a lot of study on it. but we study it as theory, between hypothesis and theory. And the only way that you can really study it is like studying a black hole. You don't study a black hole because of what you see. You study the black hole because of what it does. You study the black hole not because, oh, we're looking through this hole and we're going to measure it. No, everything that's going on around it. The magnetic field is exactly the same way. You don't study the magnetic field for seeing it or touching it. You study it for what the response is around it. All right. Take care.